Hi everyone. Oh, that's cool.
So good.
So I am Johann Lombardi from Intel, from the AXG group, Intel Accelerated Computing Group, where I'm on the GPU and the engineer working with it. And sorry for joining late. I had a lot of commitments to attend before. So today I'm going to present the update from DAOS 2.4 and beyond on the features that are coming in 2.4. 2.2 was released a few weeks ago, and I know 2.4 and the subsequent releases. We did a major roadmap update a week ago to integrate all the work with your SSD that I will detail a little bit. But this is based on the roadmap. This is the screen. So this is the roadmap starting with 2.4. So in 2.4, so we have an interesting new feature coming. So we have position support for HK slingshot. So we started to work on it on 2.2, but obviously it's not GA yet. So we delay it to 2.4. There is some work still happening to provide better performance and more stability with slingshot. Mellanox UCX, I have a slide later, but again, it's preview in 2.2. It's work within with SGA group and to be able to run over UCX and present some of the benefits of using why UCX and what are the benefits of using OPA. As you may know, Cornelis networks have been developing the new different provider for OPA, which is called OPX, and we've been collaborating with them to eventually support our own in OPX. We are able to run some early benchmark over cloud and do RPC and RTMA, but there's still more for us to be very efficient support. Multiple engine per socket with Sapphire Rapid, you're going to have PCIe Gen 5, so you will have more network bandwidth you can deliver to a single socket. But not necessarily everybody from the jump on the HDR or 400 gigabit per second network, so they might need to have two network interfaces per socket. This is why we want to support the configuration when you have two engines per socket. So that's what is also happening. On the storage feature, we have been working on online drain and integration for quite some time. So we support offline drain today and offline integration. And there have been some bugs that we have been facing that we're going to fix into the it's really related to the data placement. That is really challenging. Fault domain is a DAOS by default can detect the fault domain, but you can't specify exactly at the container level what type of fault domain you want to use for your container. That's going to be available in 2.4. Easy parity, I have a slide later. MGMT on SSD phase 1 and phase 2. I will present in the next slide. 2.4 also come with VMD support. VMD is this platform that you have on Intel CPU to be able to manage SSDs. The main thing we're interested in for VMD from our standpoint is the leg management. So you can turn over and over again. We don't really need for upgrade. You can run the VMD and support SSD upgrade. But that's still interesting for big deployment to be able to identify an SSD. So this is why we have covered using that VMD on big the rest of the feature I will detail more. So then we come to 2.6 with official support for OPX, as I said, some improvements on the releases of the distribution, depending on what is available in this timeframe. Checksum scrubbing has been doable for quite some time. It's landed on master. So this is the ability to scrub the backend continuously and be able to proactively detect checksum error, like you have with FS or CFS, even Erasure now, and support for scrubbing. This feature is landed on master, but will be officially supported in 2.6. Intel VMD, this is the other part of Intel VMD plug support. As I said, we can support SSD plug without VMD, but once you enable VMD, it takes for all required to support SSD plug. Then 3.0 and beyond, there's a placeholder for now. We have a lot of features in the world that will be developed. Multi-home network, we'll come back to this, non-implement SSD support, I will come back to this as well. Tiering is the ability to do something very similar to the storage system, where you can piggyback a container with a POSIX namespace that can be your storage API or anything, or even the cloud bucket, right? Like S3 bucket or so. So we have the data movement happening transparently between DAOs and this backend. So there's still some discussion about whether it's not need to be caching, like we want external modification of the parallel file system or object store behind the back of DAOs, and how to integrate those changes back into the container that is exposed to it. That's still work that is being discussed, but that's the purpose of the movement feature. One container, we'll come back to it. Rolling upgrade is a big feature as well. That initially we didn't want to do rolling upgrade based on customer ask. We work on it and provide a way to upgrade a 3.0 installation to 3.2 by having different server being upgraded at random points in time, and client as well. That will be a lot of change on the network protocol, and also on the overall way to upgrade existing DAO system. Delaying the grid is a feature I don't know whether it was touched during the presentation so far. In cloud environment, you can very easily start a new VM when something fails. So DAOs today, when something fails, will rebuild on the surviving node. And then when you have a new node, we'll reintegrate the node. So we have data movement on the to move the surviving node, and then data movement again to integrate the node. To move the data move twice. And delayed rebuild is this ability where when you are in a cloud environment, you can spin new instances very quickly. Maybe it doesn't make sense to rebuild on the existing VM. You just wait for a new VM to be started, and then only to rebuild on the VM that is happening. Right? So it's a kind of eviction and reintegration in one step. The data is moved from one source. There's this data streaming accelerator that is available in Interoperability and future that platform, which allows fast data movement inside the CPU. So we'll have optimization in our low-cost object code to be able to evaluate. There's more features available that I will detail into the next few slides. So first of all, rolling upgrade and what's going on in terms of upgradability and interoperability over those different versions. So in 2.4, 2.2, 2.4, 2.6, we guarantee client-to-server wire compatibility. Right, so you can have a 2.2 client talking to 2.4 server or 2.4 server talking to 2.2 client. Right, you can have heterogeneous version on the. We still require all the storage node to run the same version. So you have all the storage node to run 2.2, or they need to run 2.4, and we don't provide rolling upgrade. We don't provide rolling upgrade means that you have to shut down the server, upgrade, and then restart it. Right? You can't upgrade node randomly, and they expect production to stay up and running. That's the situation for the 2.x stream. In the 3.x stream, we will provide client-server wire interoperability, but including heterogeneous server. And the ability to go with upgrade, which is you can shut down one of the storage node, upgrade it, and then bring it back. And then you can do that over all the storage node over one period of time, and you create that one, right? So without interrupting production. That's a big feature. You know, for instance, on the stuff, it took quite some time to develop it, to get right. And I have no reason to expect it's going to be complicated. That's very difficult for them. But that's for them to try to tackle now on 2.x, and in the hope that it will work well by the time we get to 3.x. In terms of upgrade, there's another aspect to upgrade is we are enabling more and more features, right? So we see later this easy rotation patch. And as you enable new features, you need to do layout changes. And the question is that once you have upgraded to a newer version and enable some of the nice new features, you cannot downgrade any longer, right? Because if you downgrade, you come back to a version that doesn't understand the new layout change. So we have been debating internally under that. We enable the new feature automatically. No, you can't enable the new feature once you already, right? Because you want to be able to downgrade it 6.1. So we spend some time into PFS and other storage system, and basically provide a way to upgrade. We have a version for the layout, which is a set of features that are associated with it. And then we have the ability, once you have upgraded to a version, a runtime that supports this feature, to upgrade the book to enable the new feature. So it can be very small feature, like a few properties that are enabled, or it can be a pretty intrinsic feature, like I will present later, EC rotation patch. With the EC rotation patch, we store the Parity somewhere else. It's not located in the same place, same engine, before and after the rotation patch. So it means when you enable this feature, we're going to shuffle the data around the cluster. So there will be data movement happening pretty intensively depending on what needs to be moved and how much data you have in the system. So the DFG pull upgrade can be instantaneous as it is between Q4 and Q2. Between Q2 and Q4, when we're going to do the upgrade, it's like this one, right? And it's asynchronous, you can monitor it and see when it is completing, whether it's failed, and we come back to the previous layout, it's failed. But once you have upgraded, there is no way back. We don't provide currently a way to downgrade it to disable the feature. So that's the current scope. And then, as I said, in 3.x, we're going to have this official audit upgrade where things will become way more dynamic. Any questions on this? Okay. So now I'm going to get to the network improvement we're going to do. So there is two main slide improvement that we're going to do in 2.4. First of all, when we were working on 4R, we related to how quickly we were exhausting the number of clusters. As we scale the number of compute nodes, we have some nodes that were reporting that we were not, DAOs were not pre-posting in our cluster to receive messages on the engines. And actually, there is this feature that is available in different reach, which is called resiliency. So instead of posting a small buffer for each of the requests, we can post a large buffer, and then the network is going to append new messages on the buffer, and then DAOs will be notified for multiple message array. This was a way with this multi-receive feature to be able to more properly manage the buffer, and because it didn't really give us any performance improvement, it allowed us to scale better.
Yeah.
Just checking.
We need to improve our audio quality.
Okay. So, and it's not only for the CXI provider, actually it's available for all providers, supported by the DC provider, supported by the first provider as well. So we have only tested it so far with CXI, but it gives the result we expected. And we're going to test it more now with the other provider and expect some of the scalability should be addressed. And it's mostly a Mercury work done by Jerome. It's going to be integrated into the next Mercury version. That's the first change that's going to be available in 2.4. One issue is it that it's a wire incompatible change, which means that if you enable it, you won't be able to have 2.2 client. If the server use the multi-receive feature, then 2.2 the client have to be able to go to 2.4. It will be this feature. But we will still offer the ability to run 2.4 without this feature, that we can have the interoperability. The other feature we have in Fabric and in UCX as well is the ability to have memory registration cache, where for RDMA capable network, you need to register the memory in order to make RDMA. And this can be a pretty expensive operation. And for different networks, it's more or less expensive. And there's this ability to cache registration. So when you register memory, and when you are done your operation, you deregister it, there is this ability for the network middleware to not do any deregistration, to delay the deregistration in the case if later new IO use the same buffer, then you can use the buffer without scaling the deregistration. We have been disabling the MR cache, because there was a lot of issues and memory corruption actually. And most of those problems gone now, we think, and actually it's required for solution support. So we are going to enable it by default choose more. We need to do more testing and test the risk of usability at the level. Yes.
For all providers?
For all providers. So that's the two main features in 2.4 related to buffer management improvement. And that's, we also make some diffuse today. It's not very friendly to MR cache. Every time we get a new IO, we do allocate the buffer. And we do the IO, malloc, then free and malloc. So we are changing this using a pool of buffer so that when the MR cache is enabled, we have the ability to use it. And we should have a cache on the MR cache with a diffuse case. With a pool of buffer is fixed. So UCX has been in the pipe for quite some time. So this is the open source project, mostly developed by Metadata. This is the open source project, which is a competitive effort to be perfect. So one can see why do you want this, right? Why do we want to use Metadata? This is really to be able to run efficiently on Metadata hardware. Today we have the first provider, which mostly we use AXG. And we know that the reliable connection are not really scalable. They are very performant. But as you scale the number of client and server, you have a very limited number of RCG. There is also mode available on Mellanox hardware, which are called the DC, dynamically connected, and unreliable datagram mode, which are more scalable and small performance needs if you measure from a single client, but they are more scalable. And there is no way today with the verbs provider providing the fabric to use anything else than RC. So with the collaboration, we have the stack. We have been running some benchmark, and we know that when you get over a few thousands of compute node, then RC is not an option any longer. So we have to switch out to DC. So this is why we moved to UCX. We also think that probably the UCX library over Mellanox hardware is probably a better supported ecosystem. And also has some interesting feature as part of Backend that we require today when you want to use Mellanox hardware. It has native support for multi-ray, so you can aggregate multiple array of computer into a single one. That's an interesting feature that we have as well and be available. And also, if you want to use in the future, GDS equivalent on the Mellanox and NVIDIA, the GPU, this is supported in the box with UCX. So that will be also fast we can explore for those who are interested. The intent, the final goal, for us at least, not to use the verbs provider any longer on Mellanox hardware. And to use UCX, we are not there yet. We are still stabilizing on UCX. Today, I think in terms of feature, we are still like functionality and test that we pass, but it's only like 20% below the verbs provider. But mostly bugs and things we need to address in our stack. And in terms of scalability, today we have demonstrated it up to the same scalability of the verbs provider. So we still need to do more work here on Frontier. It's a preview, introduction, official support in 2.4, and then we're going to have to see on the go when we deprecate the verbs provider. It's going to happen, but we don't want to deprecate it too quickly, obviously, if there are still bugs with the UCX stack. So multi-node network or multi-provider, that's also what we call it. That's a feature available that will be available in Swift X. So basically today, when you set up DAOs, you can only use one provider. If you have, for instance, an IP deployment, today you use the verbs provider or DMA, but you can only serve clients that are using this verbs network, right? If you have like another set of clients using TCP and are for whatever reason not capable of having the infinite card, then they won't be able to access the storage system. So this feature is about being able to have multiple providers supported on the storage. This is an example here where you can have the same storage system, DAOS system, that will be able to serve requests coming from verbs interface and a TCP interface, for instance, on the working open. And you have a set of clients connected to internet and a set of clients connected to IP, and they can access the same data set. And they will have the same level of consistency between both. This is one example that will be supported here. There is also this other This other example, for instance, you can have TCP. In the previous example, I had two different networks, two cards on the same on the edge, right? The edge, two cards, so two network. But actually, you can even do it with a single card and being able to have some IP to IP gateways, right? Here, you're going to have two providers on the same card that will be able to serve requests coming from this type of client and this type of client, here TCP and here verbs. In the previous example, you need two cards. So we can support it. You can support two providers on the same card or on different cards, right? It will be tested. Any questions? Yes?
Are you talking about VPI card, NVIDIA VPI cards? Or
VPI?
Yeah.
No.
So the NIC can be the single one.
Yeah, I mean, you mean virtualization on VPI? So yeah, I mean, here you know, in this specific case, it's not like two verbs interface using two different virtual networks, right? It's two different providers. You're going to go and use the interface exported by the kernel in the TCP IP socket, right? And here we're going to use that's included.
I see you enable the RDMA for even
this is the RDMA path.
Yeah. Got you. But you can use VPI card too.
Maybe.
Yeah, because it's a dual personality.
So now on the backend feature, as you know, Octane will be discontinued after ProPass, which is the version of Octane PNAM that is available in Erasure. And DAOS has been relying a lot on Octane for the production deployment. So we have been working on this new path where, so to be clear, we're not going to deprecate Octane over PNAM. And actually, it's going to be even extended eventually to support CXL.MSSD, as I represent in the next slide. But we need to have a path of DAOS that can run without Octane on more traditional. And we don't want to do like cluster completely right, like happened when we moved to the new software stack. So we really want to really come into a way, deliver the feature over the current DAOS, the DAOS roadmap. And also continuity. So as I said, we're not going to duplicate the PNAM path. There will be a master path that will be pretty isolated inside the first layer that you can see. That will allow us to run with PNAM or without PNAM. And I will explain what it means in the next slide. We simply don't want to have significant performance impact. Right? That's the concern that I hear the most. Okay, you're going to go to Octane now, but performance, it's going to be like a traditional computer or any storage system. We have some data to support the case that I think for all the write operation, the items will be roughly the same. The latency will be in the same ballpark. So we'll be able to maintain all the performance on this side. There might be a hit on the read latency that we're still trying to isolate and to provide better number. But the read items should actually be the same. So there is performance data that we will be publishing. We have actually did a lot of simulation, but I think we're at a point now where we can run maybe a benchmark for the next few weeks. We have like all the wild imperative and so on. So we're going to provide a full benchmark and all measurements, but it's not going to be a projection. I think it's an opportunity to be able to model the DAOS hardware as well. We'll be able to run DAOS on more traditional hardware. Some CSPs, or most CSPs would have PNAM. That would be an opportunity as well to run on more environment and to support them. Everything is done in the open source. We have all the design on this wiki page. And actually, we are developing it in collaboration with engineers from HP and recently some engineers from Google who participated to help some of the activity. So it's really an open source working group. We don't publish it because I don't think we want to have a very big group here. But if you are interested in joining the party, then you know I'm happy to consider it. So this is the path today. You have this memory map file in PNAM that we manage with PMTK, where we store all the metadata, right? And the small I/O that might arrive will be stored here in persistent memory and be combined with the same PMTK information. If the I/O is big, we're going to allocate to the VA structure, and we describe what is used on this SSD. And we're going to store the data on the code. Right here, you have a link from a leaf to an offset on an SSD. And if the data is small, it is stored inside this memory map file. This is the path today used with PMDK, persistent memory. And we have been working with SSD vendors beyond Octane that are working on CXL 2.4, where there will be a memory interface, SSD, that will also give us persistency, right? You can have SSD, there's this new type of information available in CXL 2.4, where we can manage flush of anything that you want, right? The intent, so we have been working with some SSD vendor to support the same path here on the next gen SSD, CXL 2.4 that will be available. PMDK can be used in this case. We think very minimal amount of changes needed to be able to support it. Where we're going to take a hit. When you it's the performance. But with Octane, the read latency was anything you can read randomly, you had a latency of 100 and 200 microseconds. If you don't read or anything. On the SSD, it is not in the memory controller, the RAM that they have embedded in the SSD. The latency is going to be more in the ballpark of 70 microseconds. So from 120 or 200 microseconds to 70 microseconds. So you see there will be a huge hit on the read. This is going to be done because they're going to put more memory, very likely, and on the SSD, but still it's not going to be able to cover the whole space. Right? So we're going to have to do some prefetch and some optimization to PMDK to be able to get the performance out of this stack. But we are committed to doing collaboration with SSD.
You anticipate if you're working on large massive drives, and you're going to have to serialize and deserialize those drives, this is going to be one of the worst things.
It's going to be what?
It's going to be really serious because you don't have options. Right?
Yeah, so when you say the graph is our own collection of trees, right? In all those trees here, they are graphs and all this stuff. So they're going to have to be serialized into those SSD. Well, serialized, there's no serialization actually. We memory map them and we access them with a microscope, right? To be clear. But the latency of a load might be way bigger than what we see today. So we're going to use, they're going to have some caching, right, in memory, but obviously not enough memory to cache everything. So at some point, if you want to attach to it, this leaves, if it's not cached by the SSD, it's going to have to go and pull it from 3D. This is where you're going to need the latency. So we're going to have to do optimization in how we allocate the data on this memory map file. Right? We're going to need to look at it. But we are already working on it for the next pass, actually, which is the pass for volatile memory, where we need to look at it on our allocation. And this is what we are developing our own custom allocator. So this is the second pass without pillar that we are developing today that is called the Mgmt SSD pass. Yes, John?
In addition to latency, don't you pay a bigger penalty on the cache? So instead of accessing things 8 bytes at a time, you're accessing 4096.
No, because actually an operation is already, when you combine multiple bits, the tree are already at the B tree, and the B tree size is already pretty high, so we're going to still do it at 512 byte or 40 sector size. Actually, IOPS is higher because you have a better pipeline with an SSD that you can have with no store interface. You know, when you use PNL, when you do a load, the CPU wait. There is nothing else you can do. The thread, the CPU is there waiting for the data to be there. And there is no way for the software to run something else on the CPU. With the SSD, we have asynchronous interface, we're going to queue the IOPS and then manage some information. Actually, the latency will be higher, but we think the IOPS effectively at the end, when you have enough concurrency, enough clients, is going to be higher than what we get with for most reading right. I mean, when I have longer, I feel like that's the expectation, actually. But the latency will definitely be higher. So this is the other pass that we are working on currently, the non-PMDK pass, as we call it, where you have this memory map file as before, except that it is in memory. And then you have the same flow where you store the data on the SSD. The problem is that if you remove the node at that point, all those metadata goes away. And you just have the data. You have no idea what object they belong to, what is the offset. So this is completely useless. Use all this completely lost. This is what we are having all this infrastructure here, the metadata, where you're going to maintain a copy of the file, of the memory map file, of the metadata on the SSD. DAOS does everything synchronously. We receive an IO operation, we process it, we flush it, and then we reply to the client. We can't afford to keep this tree in sync on the SSD all the time, because we're going to keep the SSD endurance and the performance is going to be very bad, right? So this is why we are having this right ahead of this one, which is just a traditional journalism system, where we're going to have a very compact representation of the operation that the application wants to do and sync it synchronously to this one, and then reply it to the client. And then in the background, multiple operations that were linked to the wall will be checkpointed to this copy of the metadata we have somewhere else on the SSD, right? So the flow of an operation that we receive here, we process it by reading metadata from memory. We know the change we need to do. We commit the representation of the change to the wall, to the right ahead of it. And then when the wall has acknowledged that the IO as a committed has been written to the SSD, we reply to it. We accumulate all those changes that happen to the wall in the background. And then at some point, the wall grows, it can grow indefinitely, right? And to clear the wall, the longer it's going to take upon restart to reconstruct, right? Because when you restart, you take the checkpoint, you load it to memory, and then you have all the subtext you need to the wall that you need to apply to catch up. Right? So the idea that in the background, that was really asynchronous checkpointing, where we take all the updates we need to the wall and we flatten them on the memory map file and update them on the metadata. And once it's committed to the metadata, you can throw all the wall. And then this is your new checkpoint where we're going to start from, and you can continue to do operation at the same time. What is challenging is to have this background process to do checkpointing running concurrently, because we don't want to stay the full IO operation, right? We don't want to stop processing any IO, but the checkpointing that can run for quite some time. So we are working on the ability to be able to checkpoint and process new operation at the same time, and have a limited impact on the performance. But that's a generic decision we made at right? We decided to delay all the difficult stuff to the background and do them in the background and try to scale them. So we already have pretty advanced scheduling capability on the engine to try to run when we need the operation without impacting IO operation. So this is the one path that we are working on currently. A few details about the new data structure we're going to have. So this is the metadata of the memory map file, and this is the metadata, right? The file at the top part is the memory map file, and the metadata block is what you see there. The metadata block is the data block is operation. It's not equivalent. So into the metadata block, we have basically three types of data structure. We have the flattened view of the metadata, which is the ROS. But we also need to keep data structure that tells us what has been allocated into the file. Right? This is all the previous PMDK metadata structure that tells us what is allocated, what is not allocated. And this is those extent index that we have. And then we have the one. We need the extra data structure, because the one tells us when when an operation has completed, whether we need to replay it or not, right? An operation to the one has to be successful. If we confirm it to the one, we kill the engine and then trigger the conflict rebuild. But still, when we receive an IO operation, we might be processing the IO to the point where we might not be able to complete because we have enough space issue. We don't have enough space to complete the IO. So we need to be able to undo any changes we did in memory here before we can do it. So we have this undo data structure. So a while is a redo data structure. We log it, and then when we restart, we're going to reapply the operation to catch up and to be to the same level as we were before the crash. And we still have in memory those undo data structure that are more for when we process the IO, if something goes wrong, run out of space, or it was a conditional update and the condition wasn't met, then you have to undo any changes in them. Right? Two different types of data structure. What is important to note that the undo log that will be necessary in memory and actually don't need to be persistent. Here you have the one and all the allocator and loss. And we build DAOs, the optimization DAOs in a way where one, the copy of the metadata block and the data block, they can be on different SSD. So in the configuration file, you can decide to put all those stuff on the same SSD. Or you can have different SSD that will serve different purposes, right? An SSD just for the write-and load, an SSD for the data, and another SSD for the metadata. This type of configuration will be supported. Might not be very common, but it will make a lot with different type of SSD, QSC, TLC, and others. But this is going to be supported. Or you can have everything on the same SSD. We're going to keep this flexibility. So N2 versus V2, we don't go into much details here, but the one is basically an operation that you do only after a crash, right? You crash, you restart, you reapply everything that was committed to the one to catch up to be the same level as before the crash. Versus undo is getting when you process the operation. If something goes wrong, how do I go back to a same state? That's the two types of new data structure we are having to DAOs right now. Undo, those two types are already developed and landed to the But the layering, this MGM SSD feature is a bit of a challenge, right? How do we implement it without shaking the foundation of the house and completely screwing up the layering that we decided now 10 years ago? It's always a problem when you want software to evolve. And then we found a good story where we can really isolate and change into this VOS layer. So anything above the VOS layer, which is just a module inside the engine, everything above the network protocol, the container, the client is going to be completely agnostic to the MGM SSD feature. There will be no change. And everything under this VOS and PIO layer. So this is the stack today, DUG'22, where we have the VOS, next allocator, or human interface that basically give us access to PMDK, and then we store all the SSD information to SPDK and implement to PMDK. And this is how it evolves on the new 2.4 architecture and beyond, where basically we have this human interface that gives us access to PMDK, which is the passive day when you use persistent memory. But we are having some custom allocator. ATM is one of the options. The other allocator available that will be more targeted at managing memory, right? All the TMPFS and so on. And basically, it was two before on this side. We are writing our own allocator from scratch inside the team. It's called ATM, ad hoc memory instance code. And they're also working with HP who took the PMDK allocator, remove all the stuff we didn't need, and then going to integrate it as a human backend. And I don't know if it was presented by Lance already, they got very interesting performance results, just by removing all this. That's the new layering. I'm happy actually because it's a very isolated change. And we're not going to have too much of an impact on the whole project. Another feature we have in the 2.4 is the parity rotation. So in DAOs, you have this notion of redundancy. So you have an object, you store an object is distributed over a limited number of redundancy. And then when you store a key, it's stored inside one redundancy group. And obviously, as you have many keys, one will be there across the different redundancy. And one issue we have is that all the keys stored in one redundancy group always have the parity on the same. Different objects are completely declustered everywhere. So we have massive declustering at the object level. But for one object, if you have a single shared file that was big and had many redundancy, all the chunks that were stored in the same redundancy group had the parity in the same place. And this was problematic with some benchmark, like a single shared file, where all the parity was more used than the rest of the. So we changed that by rotating the parity inside one redundancy group. Different chunks that would be stored inside the same redundancy group will have the parity on different engines. And this allows us to, so here you have a diagram, is reference result that we got on, and it was on Frontier. So you have in blue SX is 2.4, right? This is the no data collection with this 2.4. In orange, this is Erasure code, this 2.4, right? I think there is two configurations. This is 4P2, 8P2, and each time. So you have to read and write. You can see there was this is where we realized we have a problem, right? Because on read, normally with Erasure code, there should be no impact. Because all the impact is on the right side. For read, we don't really need to read the parametric. So we had this gap, and with the EC rotation patch, we were able even to get, I think, just a little noise, but even slightly better performance than SX. Same thing for 8P2. We were able to get to catch up and provide the same performance as no-data rotation. On the right, there's still more work. I think normally with 4P2, we should have an impact of 20%, right? The parity. And I think we're not completely there yet. It should be more 190. There's still some improvement to do. And the same thing with 8P2, where it should be 20%. So we have nothing probably here. Because this is just the parity calculation, the parity that to store on the measure. So this feature is going to be available in 2.4, but as I explained, the parity is at going zero is rotating, so it might be stored and change the layout. So when you operate, you need to shuffle the parity everywhere to enable this capability. Yes?
So I understand why the rotation helps the read, but why does it help the write?
Well, because when you write, the parity is getting more used than the read, right? We're not doing first write, I think, in this example. So if you have like 8+2, you write the first two fragments, then you write the parity, then you write the second two fragments, you write the parity. For every IO, the parity is getting more operation than the data fragment, right?
You're not doing read modify, right? But
so if you do 8+2, for instance, let's imagine you write the first two fragments. So you're going to have the first two fragments and then the two parity. Then you write the next thing, the fragments third and fourth, right? You're going to write them, and then you're going to write the parity as well, right? Then when you write segments 5 and 6, you're going to write those that will be different, but the parity will be written as well. You can see different clients writing a different offset into the file. On the data fragment, they use totally different node. But each time the parity is getting used, right? So in 2.0, the parity was becoming a bottleneck. They were getting more IO and we're limiting the overall bandwidth. Whereas with EC rotation patch, the parity is shuffled everywhere, so we get different nodes and we get better aggregated values. Actually, DAOS from EC, we delay the parity calculation, right? When you do partial, I should have had some slide. When we do partial IO to this Erasure object, we use replication and then turn it into a Erasure in the background. Actually, if you do first write, then we write the full otherwise, it's replicated on the parity and then turn it to Erasure in the background. So, quick overview of the state of affairs of the middleware support. So, I presented at length in the past, I think, DFS layer. So we are improving DFS to support like end time and being more and more POSIX compliant over time. HDA5 and PIO have been around for quite some time now. That's for the Hadoop connector for Apache Spark and Parity. We still continue to test them and to maintain them. They are in a major change in the last user group. I think you presented already, Dennis. So a nice contribution from Seagate and Kuwait. So Kuwait has been, as presented by Dennis before, working on this SPDK, PDEV DAOS driving, right? To be able to re-export DAOS within the environment. And we've been collaborating as well with Seagate, as John present next, on this S3 layer, where you can re-export DAOS with the S3 protocols to the DAOS gateway. DAOS gateway initiative that was only for safe. They open it up and we can have different backend and DAOS backend to run those gateways and launch upstream to set up. There's been a new addition as well for this last year. Maybe I don't remember. We have been working with White Sky to develop this TensorFlow IM interface where you can have DFS and the POSIX layer directly connected to TensorFlow without using any other intersection or any diffuse or system model. So you can run the same way you can run Spark, that's usually on top of DAOS today, and you can run any TensorFlow IO, TensorFlow application that is using the TensorFlow API to access the dataset, can run natively on top of DAOS without using diffuse. The same way as we can use Spark. We continue to work on the ecosystem by growing with Segway, with Lombardi, Middleware, with AXG, and so on, working on the data acquisition system for the next generation Atlas experiment. Right? We have to stream the data to DAOs and process them in real time. That's the evolution of the software stack, the middleware. A few improvements that we got into platform. Today, Fuse is single user. When you mount a container, you mount it as a regular user, and you can only access with this user. If another user wants to access container, they need to mount it. There's no multi-tenancy in the Fuse user. And in 2.4, we have landed this feature for 0.4 by 7.9, which is called multi-user diffuse, where you can mount as a root a container, and then have multiple users writing and editing files from the same. Right? Then at that point, obviously, the different user can have to use Unix permission inside the one point, which is pretty common for other devices. You can still do the intersection library as well, projection. There is only one limitation that when you run diffuse with your own user ID GND, there are optimizations that the handle, the container handle, is shared between diffuse and the application. When the application starts, it's going to talk to diffuse and tell, oh, I'm going to use intersection library, give me your open handle. And then it can share it between diffuse and the application because they are using the same user, so the same container handle can be used. Here, you can't do that, right? Because diffuse is implementing a root that is own handle. And then any random user might want to use the intersection library, but they need to connect to the container by themselves. So they will still do the system call, and diffuse will also be applicable to multi-user mode, multi-user mode. So you can't share the handle with me. You're going to have to connect to the container by yourself from Userspace directly from the intersection library. So potentially more connection will have to be done if you want to use the intersection library with the multi-user or the diffuse. So we got some statistics some more ago. There was a poster at SC19 comparing POSIX among all HPC applications, which are the ones that are using traditional read-write operation versus using the streaming function. And actually, I think it was 50-50% case. So we learned from this, and we decided also to intercept the streaming function in the intersection library so that we can cover all applications. The limitation is that usually with S3 you have caching. In our current implementation, there is no caching. So when you do S-write to a file, it will hit the wire. Right. Still a feature you can disable if you want to use another variable. We have also been working on some improvement for some AI framework. We realized that we're working on this TensorFlow IoT code that we did at ISC. There was many cases where we say AI framework were scanning the dataset again and again, totally independently. Every process do redir start over the tree. Even if you need it to do only once and share it with API, they are not doing that. So every process was scanning again and again and again. And having no caching on the compute side was a problem, right? Because if you have a node with 100 ranks, each of the ranks was scanning the tree, and DAOS was hitting the wire all the time again and again. So some caching on the client side might be helpful for those use cases. So we had a stable feature to do pretty aggressive caching for those AI framework. This is read cache, and so you see some of the results we did with the Erasure to the next slide. So we have been more than we've been working closely with LRC for the next system that we're going to install there, and we're going to do some benchmarking there. They have a custom benchmark that to emulate all this AI framework, I will work. And this was developed by Guido, the Parkwine, and Nicolay. We have the default result with DAOS 2.4, we get nothing, and then 2.4 when we enable all the caching feature. So this is with one client, effectively, before the caching and after the caching. So we include on the thread, you can see that performance remains flat without the caching as you would expect. Right? The caching is working pretty well. This is the line blue line, and this is the time it takes to load the data set on the line. We've got pretty constant time, otherwise this exponential time is very increasing the number of processes. And we need to for large files in 5 to get the benefit of it. And then it's because it works as you increase the number of clients. We see of course different clients who have no caching, show the client to fetch the data set. But effectively we're benefiting from this massive multi-thread caching as you have on one we're pretty happy. So one container is a feature we'll be working on. So again, lessons learned from working on all this application. We see that there is many read-only data sets. And there are optimization we can do in layouts to better serve read-only data set. Going to one container, right amounts with many containers. And the optimization we can do is like the size. Just now I've been trying to run to develop size on NDS for quite some time. And this is a very difficult feature to do in the general use case, right? You have a control divider. And actually we decided not to support it, but instead have this notion of read-only container, and then you can very aggressively cache the size in the item, right? Because you know there will be no control divider. So we're going to do this size on NDS implementation by labeling the container as read-only. And then we calculate the size and store it on the inode, and then you can scan the file system pretty quickly by measure from frame per. We're going to do some optimization on the layout with us, where we know that with no concurrent update can simplify the epoch mechanism. We have this pretty complex versioning system that might not necessarily make sense if you know that the data from where we need to maintain all the community control aspects. We will simplify all those aspects. And also, as those AI framework, they scan the data sets actually, but what we're going to do is instead of doing the scanning, we can create a specific key value store where we have an index of 45. And we're integrated with PyTorch and TensorFlow. But instead of them reporting to POSIX code, stat, we can just give them the file straight away. With the small index, we maintain with a custom key value store inside the container. But we accelerate this startup time, which is pretty substantial today.
So,
yes.
By having this index, you can eliminate the need of using a metadata management application, such as the old one, Hyrox, for instance, and the friends, right? Okay.
So I have two more slides on future direction. So where we're going to go eventually, we start to intersect more and more code, right? We start the streaming function, and my goal personally is to intersect everything and to be able to run completely without fuse, and be able to intersect all system code and have full support of POSIX completely in Userspace without using the kernel. There was a problem before about how to use the nmap, but now there is this user full FT capability in Linux kernel that allows us to do nmap intersection in Userspace. So that would be the direction. Yes.
What's the performance implication of using this versus the one using DFS? That is the native one. I understand that the DFS provides only partial POSIX, but this one full.
Well, here it's a context of DFS. Here it's DFS. It's just a POSIX interception. So we will be using DFS. We know today we have this interception library and diffuse, and when we load the interception library, then we don't intercept everything. The stuff we don't intercept, we send them to the diffuse, and you go with the slow pass, right? And what I'm saying that I want to intercept every code, including metadata code, file information, and details, everything, and remove the need for diffuse in this case. Obviously, then the problem that we can tell you in the previous slide, you mentioned caching, and caching is not diffuse. So if you intercept everything, then you see you don't have the caching capabilities. This is why it's combined with this other stuff, and we'll have to implement this collaborative caching across all processes working on the same node by using shared memory. So basically, we'll be re-implementing to some extent the Linux page cache, the user space across all the processes and threads that are collaborating on the same. Right? And I think this is, for me, the ultimate solution where we're going to get pretty good POSIX compliance and without leveraging the kernel. So we see this is a lot of work, and we are going to get there incrementally. This is why we need to streaming function first, and we can do some of the metadata function, then we implement this caching capability. It's going to be available slowly, and this is the ultimate goal. The other direction we're going to take is the ability to do active storage, where basically you can ship some of the data filtering capabilities to the storage node, right? Instead of scanning stuff synchronously on the client, you will be able to describe the processing you want to do on the node, you send them to the storage node. We are demonstrating it today with POSIX Find. You can run Find partially on the server side, and we also have a IATP engine that can work very securely on the but there will be more and more use cases over time for this and the API. We're going to implement the GPF as well. You can have a custom script, you can sheet and run it on the server side. That's an active area of development currently.